Please, could you sit down now, because we have to start. Welcome everybody to today's seminar on sea-based measures to reduce the consequences of eutrophication. This seminar is organized by the Swedish Agency for Marine and Water Management, the Ministry of Environment and Stockholm University. My name is Christoph Humborg. I am a professor in biogeochemistry here at Stockholm University, and I am also the scientific director of the Baltic Sea Center. And I will chair the session today. The Baltic Sea Center has been founded some 2 years ago, and this consists of the former Stockholm Marine Research Center, the Baltic Nest Institute, and the Baltic Eye think tank project. And we have the clear mandate to communicate science to decision makers, to the society, and we will analyze and synthesize relevant information, environmental information of the Baltic Sea, and communicate it. And this is, in a nutshell, what we will do today. And let me say some words on sea-based measures and how I see our role as scientists in this. In science, there is no last word. We cannot deliver the truth. What we can deliver in science is an approximation to reality, the best available knowledge. But how do we deal with this best available knowledge when it comes to sea-based measures that has been really vividly discussed in the media, but also in science? One side of the coin is that we know that we cannot be so sure about the large-scale effects. There are certain risks if we do a large-scale measure. On the other hand, we all agree that there's not a single square meter in the Baltic Sea that is not manipulated by man. One more issue I would like to say in the beginning here. We will hear about very interesting projects and very interesting results. Some of them are large-scale measures addressing the anoxia of the central Baltic Sea. And some of them, there are small-scale measures, mostly located at the coast. And sometimes we see in the media that these both methods are compared with each other. But I think this is wrong. This is a personal opinion, because let's take the example of cleaning of sewage treatment from households. This will not cure the central anoxia of the Baltic Sea. This we can do a simple back-on-the-envelope calculation. But on the other hand, it is very important to clean up a local bay for a community. And I think it is dangerous to just compare these measures. I would say they are different. And this is, I think, really interesting what we will discuss today. I'm really looking forward to very interesting and vivid discussions today. And with that said, I would give the floor to Stefan Berggren from the Ministry of Environment. Please, Stefan.
Thank you. I'm just going to say a few welcoming words and in some sense also echo what you just said. So very welcome to this seminar. This is a cooperation between the Ministry of Environment and Energy, the Swedish Agency for Marine Water Management, and the Baltic Sea Center at the University of Stockholm. And it's also as a contribution to the regional work within HELCOM, and we're also very glad to have HELCOM here today. And it's a really pleasure to see there's so many interested in this topic. The seminar is heavily overbooked, and it's the last I heard 140 people participating, which is much more than we anticipated when we started to arrange this together with the other organizers. And there is also people from other countries here. We are very happy for that as well. And we are recording the seminar, and it will be put on the web to facilitate the dissemination to interested persons not able to attend the meeting. And combating the eutrophication of the Baltic Sea is one of the biggest challenges we have today. to save the Baltic Sea and the environment in the Baltic Sea. During the 40 years of HELCOM activities, considerable progress has been made, and the load from industries, wastewater treatment plants, leakage from agriculture has decreased during those years, but there's also a lot to be done, and we need to improve the measures when it comes to algae bloom and dead zones, for example. And we have continued to reduce land-based sources, but we also need to see other ways to speed up the recovery of the Baltic Sea. And that is on the agenda today then. Some scientists argue that it takes 50 to 100 years to achieve a clean Baltic Sea. And that's a time frame relevant to our children and to our grandchildren. But it's not always in line with the times, with our times quarterly economy. And that is quite a challenge for all of us, I would say. Reducing the internal load from the Dead Sea bottoms and recover nutrients from the sea can provide complementary improvements. And Sweden has invested a lot in research and pilot projects to test a number of alternative ways to improve the environment state of the Baltic Sea. And we're looking forward to hear more about that today. And the purpose of the presentation today is not to have a discussion on pros and cons of sea-based measure, but to inform about the experience so far. What methods can be applied, both at offshore scale, but also within the local level in a smaller bay. And we will also have a panel discussion with well-recognized international experts on the potential and risks of these measures. And we would also like to encourage everyone to write down their thoughts and ideas triggered by the presentations. And we will collect comments by email for 1 week after the conference, and it will be considered when we follow up the seminar. And I would also like to just echo the need for communication. We spoke just during the coffee before. The need for communication when it comes to science and to reach out to policymakers. It's very important that we have a good dialogue so that we can make good decisions based on scientific results. And finally, I would like to thank the University of Stockholm, the Swedish Marine and Water Management, and all the presenters, all the participants for organizing and being part of this event. And I'm looking forward to some very interesting presentations, and well, that's about it. Thank you.
Thank you, Stefan. How is this day organized? And these are the welcome notes. We have done that. So the program. We start first with a scientific background. And to do that, I would like to explain you a little bit how we agreed about this scientific background. We invited a review panel, an international review panel, to give their thoughts about how does the Baltic Sea work, how does the eutrophication and the nutrient cycles, oxygen cycle work in the Baltic Sea. So this will give you a scientific background that Bo Gustafsson will present. And later on, we will have then the presentations of the various projects that have been financed by the agency or by private foundations. And then we have lunch break, and then in the afternoon we have parallel presentations. There will be also presentations of projects, but they will be done in these rooms, these satellite rooms here on the Degersal, the smaller rooms. There will be like 5-minute presentations of poster-like presentations, and they will be given 5 times in each room, so to say. So this is the idea of today. And then we will have Lena Victorson will then, working for the Baltic Eye project, will give perspectives, a kind of summing up the projects, what's in an essence, and a summary of these. And this will be then the basis for the panel discussion in the afternoon, which will be led by Susanna Balczewski. So this is the idea of today. Then, as Stefan already said, we want you really to be active in this, because I don't think that we have said the last word. It's not only in science there's no last word. I also think on these sea-based measurements there's not a last word. This discussion will go on. And your vote and your opinion really matters. And as Stefan said, we will continue. You can write, email your opinions about this day. We will also have note blocks here that you can write that in here. Shall we distribute them, Helena? They are distributed in your package, I would say. So if you have any comments, please write it down. They will be really evaluated and taken seriously, these opinions. You can also tweet them if you are able to do that. And then we also will do a Mentimeter, but this is by far too complicated for me. So Helena will explain you how this will work.
Yes, to just underline the idea that it's important. The important thing going on here is not only what is said on the stage, but actually that you are all here. And we're going to show that by doing a little vote. So if you take up your mobile phones, and if you don't have a smartphone, don't worry, sit back and relax. But I think most of you do, and you all got the question if you had internet access and got a card to get it. If you don't, I'm not going to answer any question on how you get on the Wi-Fi. That's you solve it, or otherwise you won't be in the vote. And then you go to the webpage govote.at, and you enter the code that is shown there. And let's just. I'm just going to get up the results as well. That's why I'm.
Yeah. Yes. Better than we.
The code is 201857. And 201857. Two 01857. Sorry. Should have tried this before. Sorry, some technical difficulties there, but we got the results. You can still keep on voting. So, you're a big mix of people in the audience, and it keeps on changing. But as you can see, it's a mix of local authorities, academic organizations, government, national authorities, and NGOs here today. So, I think just the fact that you're brought together is important. And if you just figure that out, if you just figure that out, then it's time for the next question. What are your expectations for today? And here you have the chance to shape the answers yourself. It's an open-ended question, so you can type in your expectations. Is it still saying not activated? Okay, I'm sorry. Then we leave this and we take the expectations after lunch, because obviously you should try again before you do that. But you can think about it and then you'll get the question again.
Okay, before we start, 2 practical issues. So for anybody who has to go to the restroom, it's 2 floors down. Then we will have not a coffee today, but we will have lunch that will be served. And for those of you who requested some special food, allergic or whatever, there are name tags on them. But this will be then during lunch. Okay, with this said, I'm looking forward to a really interesting seminar today. And please, Gustafsson, he will give us now the background.
Thank you. I hope this technology works. Do you hear me? Yeah. Good. As Christoph said, we started preparing this background with also a scientific advisory group around it, and they gave their thoughts. After that, we have rather slimmed the presentation again, and we will see the response from the scientists afterwards if we and then we will try to continue with a summary of this after the workshop. So today we will have the focus, I think Stefan already mentioned, the focus of what the Baltic Sea would look like for our children and their children in turn. Well, the children of today will probably remember some of these pictures, or if they live in certain areas on the Baltic coast, also experience it. And I know that my daughter experienced bathing water which had about 2 decimeters of visibility the other summer when we went to the sea. What we see here is the blooms, and I think that is the most prominent visual expression of eutrophication. These pictures are worldwide known with the cyanobacteria blooms. And these are a result of excess phosphorus contra nitrogen during summer. In combination with warm water, these blooms can form. And their speciality is that they fix nitrogen gas instead of using inorganic nitrogen nutrients. There are some hopes in that there is commitments for a long-term goals of getting a good environmental status, both regionally in the Baltic with HELCOM countries and higher? Yeah. I will try to speak higher. I saw something in the back of the room. But also in EU, and so for all regional seas, all seas in Europe should reach a good environmental status. And what is a good environmental status? That is something we define. It's a combination of science and our expectations of what we want. So here are examples of benthic macro vegetation, eelgrass beds you want, and no cyanobacterial blooms. I will now show just a brief illustration of from a model simulation. That is, where's the mouse? That we did a couple of years ago, that shows the development of hypoxic areas in the Baltic the past 100 years. And what you see here is that it's been really an increase in these anoxic and hypoxic areas during these 100 years. the reason for that is our anthropogenic pressures. One of the big ones is the increased population, especially the urban population. Population in general in the Baltic have increased with 50% during the last 100 years, but the urban population have increased with 400%. And simultaneously with that, also development of water sewage. Remembering that 1 person equivalent is about 1 kilogram of phosphorus and 4 kilograms of nitrogen, you can see that this is a lot of nutrients. Luckily, we take care of a lot of that today. Oh, wrong way, sorry. Another major change is the agriculture. The agriculture have increased in intensity and also with that fertilizer use. And if I toggle this a bit back and forth, you see the change in agricultural area from 1900 to 2005. And the resulting nutrient load trends from this look like this. And what you see here is that around 1980, the nutrient load peaked. And then we have seen significant decreases in the Baltic Sea, especially in phosphorus. Most of this is the sewage treatment in coastal cities. Phosphorus loads, when it peaked, was, we think, about 3,000 tons to the small Öresund at one point. Now I think it's 50 or 30. So there is significant progress, but still the Baltic Sea is not very healthy, and to understand why that is, we need to cut up the surface and have a look at the conditions below the surface. And we know the physical setting of the Baltic Sea. You all know it's for us that comes from the west coast, we know the concept of fjords, and the Baltic Sea is a major fjord which in the Norwegian sense at least is defined by something deep with some shallow and narrow mouth. If you're a Dane, you might have a different opinion. So this morphological constraints of the Baltic Sea is really limiting the exchange. And in this just sketch of some sort of stratification, we see that these deep basins are then filled up with saltier water. And on the top, we have a large supply of fresh water. And this combination creates a strong stratification that hampers exchange. So if we look a little bit in detail on how the circulation works in a deep basin like this, we have these ones are illustrating mixing. And so there is an influx of salty and hence dense water that comes in through the straits and follows the bottoms and sinks to some level where it's interleaved into the stratification. The amount seen over a long time decreases with depth. However, in one inflow, the actual flow will increase with depth because you have a mixing into these currents of ambient water. So very salty water comes in, it decreases in salinity, increases in volume flux until it's interleaved somewhere. It's more frequently exchanged up here than down here. In the other process, that supplies exchange matter in this deep basin is the mixing. So there is an ongoing mixing that tries to level out all gradients. So if you would leave the Baltic Sea without any inflows and without turn off the freshwater supply and turn off the straits, it will eventually become homogeneous in salt. These inflows also makes a continuous rise of the water in the interior. If we add oxygen on this, as some grayish stuff here, we will have organic matter sinking through the halocline here into the deep water, and when that is decomposed, it will consume oxygen, or when oxygen is gone, it will use sulfate and produce hydrogen sulfide. Hydrogen sulfide will be later shown as negative oxygen. You can convert between those. And oxygen is then supplied by these processes that you can have inflow that actually replaces water with water with more oxygen, or you can have this mixing that tries to level out the gradient between high oxygen up here and low oxygen here. So actually, the longer a stagnation period goes on, the more hydrogen sulfide you get down here, the more oxygen will actually diffuse down here. So we will have a balance in the end, but that takes a long time. To illustrate a little bit these events in action, I will show a model simulation now. So in the top here, you have a transect from Kattegat to the Gotland basin. Now, this is based on our model Baltzan, which is actually a basin scale model. So therefore, there's no gradients within these basins, but rather horizontal lines. You see oxygen here in the top in colors. Here you see the salinity at the sill here as a time series. And here you see salinity, and the colors were really bad here. So it's salinity and oxygen in the Gotland deep basin down here. It doesn't matter because oxygen and salinity is approximately the same curve. So, and then we will see if I can start the movie. And it's then we're trying to simulate the inflow that occurred, started on, I think it was December 11 or something. Where is the... There. So you should look out for when this pulse comes here. Then you will see that oxygen increases successively in the basins. So now the inflow started. Now it's already the first reached the deep, really deep pits in the Gotland Sea Basin. It fills up with more and more water. So the anoxic old water is pushed up. And since the area increases with decreasing depth, it will be compressed, the old water up here. And it goes on with, we guess about the future weather this year until the end of this year. And then we see it's still quite anoxic up here. The oxygen concentration in the really deep is barely oxic. So it will be we will have to look at this movie a year from now and see if it's anywhere near reality. Okay, now into the nutrient perspective. So I will show some tons now. And first, we take a look at nitrogen. There's lots of numbers in these now. You shouldn't pay attention on the decimals here. but I will try to highlight some major things in this. So first we look at nitrogen. If we sum up how much nutrient that came in the last 100 years, it was about 80 million tons of nitrogen in 100 years. But we see out of these 80 million tons, that resulted in an increase in the total amount of nitrogen in the Baltic Sea. All these numbers are total for the whole of the Baltic Sea, to simplify things, of about 0.5 megatons. And then there is an additional increase in the content in the sediment. There is nitrogen in the organic the organic matter in the sediment as well. That's 5 megatons. But most of it has been transferred either to deep in the sediment, but primarily denitrified. Denitrification is a process which converts the nitrogen that can be used in that cycle in the biological pump into nitrogen gas. So it's a very efficient removal of this nitrogen. If we look at the same for phosphorus, we estimated that it's about 4 megatons of phosphorus that has entered the Baltic Sea the past 100 years. I think it was something like 2.5 would be the excess compared to what could be maybe called an anthropogenic load. We see the increase in the water column has been roughly half a megaton, approximately the same as nitrogen. Most of it has gone somehow into the sediment, and only a very small proportion, 10%, have left to the Skagerrak. In the sediment, it could either be buried, with that is meant that it will never return, basically, or be in some sort of active sediment pool. This is a model based on model experiments, so of course one could argue the division between those. So how does this work then? So when we increase the phosphorus input, you will get a little bit increased production. Some of that will end up in the sediment. And then of that content in the sediment, so the very simplest description of burial of nutrients in sediment is that you have an accumulation in the sediment. You add continuously material on the sediment, so the sediment surface basically goes up. And then different kinds of matter in the sediment will then gradually go deeper in the sediment. And the very simplest description on how much phosphorus is being buried is to take a fraction of the concentration you have in the sediment. Say the fraction E. So if you have a concentration Y, E times Y will be buried, but the rest will be released eventually when you have a steady state. But if you have a closed system, if your external input changes, this will increase until your burial is the same as the input. So if you have a lot of phosphorus coming in, you need a lot of phosphorus in the sediment to get a lot of phosphorus out. But then since E maybe is a very small number, this will be very large. So you have to circulate the phosphorus a lot in the system. And then you get lots of algal growth, etc., to get it out. I will illustrate this with just a few numbers. As I said before, taken from a model, right or wrong. 1900, 16 kilotons per year in, 14 out, 0.5 to the Skagerrak. And then you had a circulation here of about 100. So going to 1980, that was the peak of the load. So we think it was about 70 kilotons per year coming in. At that point, only 30 leaves. 200 cycles. And this is up by a factor of 2. But even though this is only up by a factor of 2, this pool, we don't get rid of everything. So this is still growing, which you can see that the difference between those is 50, and this is 30, so this increase with 20 kilotons per year. And that actually happened in the model between somewhere in the end of the 60s up to fairly recently. So if we go to 2000, then we're closer to even here. So it's getting closer to a balance. But if we start to reduce here, what would happen? This will go on for a long time before it reacts and starts to reduce the burial. So therefore, this creates a long time scale in the hole. And you see we have 1,600 tons in these sediments. If we go to the pelagic, have some similar picture. So here is what comes out from the sediment. Here it was sedimenting, but now we added also what goes from organic matter to nutrients in the water column and what is uptaken by plankton. A very simplified system. Now you also see I split the loads here because a part of the load is organic and a part is inorganic. Especially sewage, you have also untreated sewage. But also from land, of course, you have lots of organic matter. So in 1900, about 50-50 between these two. So half of it went to the sediment and could be exported, and the other half went turn more into the cycles in the pelagic, creating algal growth. Of course, some of this was returned here that way as well. Then we go to 1980. Now this arrow is twice as big as that one. The differences between these plots are so big, so we didn't manage to make arrows proportionally. So, so now twice as much is going just around in the water column as going to the sediments. But also this is much larger. So you get an amplification all the time of the production. And if you go to 2000, then we have 1,000 here. That is 10 times more than 1900. So here we really got a very, very strong amplification of the pelagic recycling. And this is due to what I touched upon before, that phosphorus has increased in tons since 1900, approximately the same amount as nitrogen. So you increased the phosphorus excess in the Baltic Sea. And the spring bloom in the Baltic Sea, that is limited by nitrogen. So that means that the spring bloom has not changed that much, leaving nutrients, phosphorus left for the summer. In the summer, we can add a little bit more nitrogen, but we also have warmer waters and more stable waters. We can have a much more efficient recycling of the nutrients during summer. Now, this is model experiment, so we don't know if these are the correct numbers, but I think the mechanism is correct. You get, and this is further enhanced also by the increase in hypoxia in this period. Partly it's one of the reasons behind the lower nitrogen and higher phosphorus, but also it enhances these cycles. And that's what is known as the vicious circle. So if we look a little bit closer to the sediment processes, the phosphorus sediment process related to what happens when it becomes more or less oxic. So 100 years ago, we had a relatively little organic matter coming down. It was relatively oxic, also in the deeps, not completely in the really deep holes, but that is really small areas. But the majority of the Baltic Sea, it was fairly oxic. You didn't have a large storage of organic matter in the sediment, which is also a cause for changing these, reducing, how do you say, making the sediments more anoxic if you have organic matter in the sediments. And in this case, it's shown that in the organic part of the sediment, you can store more phosphorus per molecule or per carbon. So the carbon to phosphorus ratio is lower, so you can relatively efficiently store organic phosphorus. You can also store inorganic phosphorus relatively efficient in oxic. If we go to the anoxic, which is the case in many sediments today, and it's not only, I think, personally I think, it's not only when you really have anoxic, as it says here, but also when you have oxic water, but very much organic matter in the sediment. Then you also get difficulty with. So in that case, you can only bury maybe a third of the phosphorus per carbon compared to the oxic. You also get much less mineral inorganic phosphorus buried. Now one of the questions is what will happen in the future? Is it possible to look back and compare with the future? Because this will, in the future, even though we get better oxygen conditions, still the organic matter flux will be different than 100 years ago. We have today a big storage in the sediment of not only phosphorus, but of course a lot of organic matter. What's happening with that? And especially how would this inorganic part develop in the future? That's, I think, is the frontier of research, you could say, today. Coming back to what the future again. We have here in Stockholm University at Baltic Nest Institute, we were involved for several years, very long time, to model numbers on how much should we reduce to get to the Baltic Sea that we want. Now 1.5 years ago, there was a new set of figures that I was involved in the Copenhagen Ministerial Declaration, where we said that we needed to reduce about 100,000 tons of nitrogen and 15,000 tons of phosphorus. Now I'm actually involved a little bit now also in the follow-up of this, and we see there are promises. What has been achieved since this reference period used in the BSAP is 1997 to 2003, and the latest numbers we have now for 2010 to 2012 shows that we actually achieved a lot on nitrogen here. It's a significant nitrogen load reduction, but also phosphorus inputs have reduced rather much. The question is, of course, always it will be more and more difficult the closer we get to these targets. But there are some hopes. And I know that there are people in the audience working with this, how to implement these measures in Sweden. But one other thing is that this will take time, even if when we manage to implement these measures, it will still take a lot of time before we have the really clear water in the Baltic Sea again. So I think this is the key, one of the key elements for today. The time scales, the long time scales, can we do something about those? And what will happen to this little guy or girl in the future? Will she see it, or will it be future generations after that? Thank you.
Thank you, Boo. Now it's time for some questions and comments, and maybe I start with one comment or a question, Boo. You mentioned that there is. You have to. there are some 2 million tons of phosphorus accumulated in the sediments, and very often this is said that this is the heritage of the phosphate of the phosphorus pool, and we will discuss a lot with it about. And sometimes we compare this pool, this internal pool, which many people call it, with the river loads, and saying, okay, the river loads of phosphorus is about 30,000 tons, and maybe we can reduce it annually by 2,000-3,000 tons if we do our best. But there's a pool of 2 million tons in the sediments, and of this, about 100,000 tons can be released if it gets anoxic, and when it gets oxygen, it can be precipitated again. But I think this comparison is sometimes a little bit misleading, because we have to compare pools in the internal in the Baltic with the pools on land. And these pools in the agricultural soils are about 50 million tons. So there's a big, larger pool sitting out there. So it is not only the question about the internal pool. I think also in the discussions today we have to think about what sits and waits for the future in the agricultural soils. Maybe you would like to comment that, or? Yeah. Okay. Okay. But let's start with question now.
Thank you, Matthias Bergman, Baltic Sea Action Group. You said that, if I did not catch this wrong, that when you decrease the input of phosphorus, which we have done now, you actually also decrease the burial rate of phosphorus in the sediment. Was that correct? If so, what's the mechanism really there?
I mean, initially nothing happens in the sediment, and that's what's leading to what's called the internal load. I mean, that's where it comes from. It comes from lake science, where you reduce the input, and then the nutrients continue to cycle for a while, because you only. So what you do is that you reduce the sedimentation a little bit when you reduce the loads. But that is very little. I mean, if today you had a sedimentation, I don't remember the numbers now, maybe 300 tons, and then we say we reduce with 3,000 tons, then you reduce the sedimentation with 1%. And then that reduced sedimentation will then go into the sediment pool and eventually make the sediment pool a little bit smaller. And that will eventually reduce the burial. But it's a slow process. That is the key thing. But it's also a very simplistic view, this. I mean, in detail, it's a little bit more complicated. This is
that was my question. But we can maybe check that later.
Yeah. But it will not decrease the burial immediately. Instead, maybe you can get an increased burial in reality, because in some areas we'll get better conditions. In shallower areas, you can get better oxygen conditions, and thereby actually increasing the burial and increasing.
Yeah. Okay, so it varies. Yes. Okay, thanks.
Okay, I think the next was Peter.
Okay, Peter Wallenberg, LF. Question about how to tackle future climate changes. We all know that there will be heavier precipitation and warmer climate, so the natural runoff will increase, and not really matter on what we're doing on, for example, agricultural practice. So what will that affect? I mean, when we are trying to reduce the phosphorus impact, but the climate is struggling against us, and how do we tackle that?
I wished I had a positive answer, but I don't know actually, because most of our evidence points to that we have more difficulty with these processes in a warmer climate. That the Baltic Sea will be even more prone for hypoxia, for instance, in a warmer climate. So it's a difficult struggle, but so I don't have an answer actually. An umbrella over the Baltic Sea, maybe.
Yes, Maria Lamonen from Ministry of the Environment in Finland. Thanks, Bo, for the presentation. I was particularly interested in your simulation of the inflow from December 2014. What about, since oxygen conditions are so important for this phosphorus cycling in our system, do you have any idea what this major inflow that we have now had in end of 2014-15, as well as we have already had some inflows in 2014, when we know that in 1993, when we had a major inflow, that reduced the phosphorus pool in the water about 40%. I think that was Swedish scientists showing those figures. Do you have any idea of what these new inflows will do to the phosphorus store in the water column?
I think well, it's difficult to say, but I mean, if it's, now this is one simulation we did very quickly now, so I don't know how much to trust it, but but according to that, not much happens actually, because it's still so hypoxic. Even after this inflow, it seems from the simulation that the hypoxic area is the same. You barely go oxic in the deep, and within then a year or so, it will be anoxic again. Then it would maybe even be bad for the Baltic, as the 2003 inflow eventually, I think, led to very high phosphorus concentrations in 2005, which resulted in the worst ever blooms. So it's difficult to say. But one important thing is that we have seen major changes in Baltic Sea hydrography on a decadal timescale. And when we did these very long simulations for 100 years, we see also changes in 50-year timescale. That the first half of the century was much less saline than the last part of the century, for instance. So it could be that we enter a regime where you have a lot of inflows, and then things might start to happen. If we have this kind of inflow every year, because now we start from a really bad situation. We have very, very low oxygen concentration, and the sediments are completely full with organic matter just waiting to be decomposed. So,
well, thanks for the reply. I just want to, I was asking because I was in fact looking at some fact sheets from IOW in Germany, which they released, I think, in the end of last year, and they are in fact showing that in the southern Baltic up to the Gotland Basin we would have already better conditions, oxygen conditions in the bottom.
Yeah.
Further questions? Please, more comments. Okay.
Barry Broman, retired oceanographer from SMHI. I wonder, is there any possibility to find a way to make inflows more often? Because if you get a major inflow, then it will take years for the next one. It will take 20, 25 years or so. If you get it, say, every second year, then it would be a good thing for the Baltic.
I mean, without going into a lecture in oceanography, I think what I said before when I did have lectures around this, I said that, well, maybe it's a good thing to put some dams in so you don't get it so extreme. So if you compare to the White Sea, that is approximately the same bathymetry as the Baltic Sea. It's 450 meters or something. It has a sill of 20 meters, which is very long. And it's completely oxic all the time. And the reason why it is that you have lots of tides in that area, which we don't have in Kattegat. So if we had very strong tides in Kattegat, so we mix the water all the time, the salinity would be exactly the same every inflow, and every inflow would go to the bottom. It's approximately like that in Botnian Bay. That's also very well ventilated, although you have a still. So even out everything, and then it will different.
Further questions? Okay, thank you, Bo, very much for this very comprehensive and very good summary. And I think really this gives a good background for the further discussions that we all are up on speed here.